Okay, so now let's get on to example one and let's actually apply some of the things that we learned. It's really important for us to understand that the transformations of the function doesn't really matter on what the function is. Now, obviously, all these functions are completely different, right? But notice that the notation that I'm using for my functions is like an f of x. So it doesn't matter if it's f of x or g of x, but all these functions are, the operations are going to be applied the exact same. Now, when I'm first understanding all of this stuff, usually what I prefer to do is, or at least like for these first three, what I'll do is I'm just going to label what we have, all right? Now, in this first example, it's asking us to identify the transformations from the parent graph and then determine the domain and range. So for educational purposes, I'm going to label what I have. And then, hopefully if you still like that method and you want to continue doing it, that's fine, but I'm not going to, go over that every single problem just because it takes a little bit of time. So here you can see like the main idea, and actually did I write in those steps? Oh, I guess that's pretty good. So I guess I could probably add in some like kind of tips. So what are the first things we want to do? The first thing we want to do is identify what the parent function is. So my parent function in this case is going to be f of x equals x. Now, the next thing I want to do is identify what values is happening to the graph. Well, you can see that I'm multiplying by a negative, which is like the same thing as -1. So I can say a is equal to -1. Let's actually zoom in. A is equal to -1. And then also remember that looks like x minus 1. So just like how we have x minus h, this is being x minus 1. So I can say that h is equal to 1. So now that I know that my a is -1 and my h is 1, I just kind of go back to my definitions. I go back and reference them and say, all right, so when I have a was less than 1. Okay, it's a reflection. A is actually equal to 1. So it's not going to be a vertical stretch or compression, but it's going to be a reflection about the x-axis. And then my h is my horizontal transformation. Just remember that the formula is x minus h, right? So, and that's exactly what I had. I had x minus 1, so therefore h is equal to 1. So now I can label my transformations. I can say it is going to be a reflection of the x-axis. So I can say reflect the x-axis. And I can say this is going to be, since 1 is positive, I'm going to be shifting the graph 1 unit to the right. So I'm going to say shift 1 unit right. Now, I decided to make this problem a little bit more interesting by not only identifying the transformations from the parent graph, but then determining the domain and range. So let's go and look at the quadratic again, and just to kind of make sure that we understand. I probably could have written them in there, would have been a bad idea, but here you can see the domain is from -infinity to infinity. So therefore, if I'm shifting the graph left or right or up or down, actually it really doesn't matter what I do. There are no restrictions on the domain. So the domain is always going to be -infinity to infinity. However, when I reflect this graph, like if I reflect this about the x-axis, I'm going to now shift this graph is going to be now facing down. And then I think I said shifting 1 unit to the right, right? So the graph is going to look something like that. So the domain is still -infinity to infinity, but you can see the range is now going from -infinity to 0. Now, you didn't have to sketch the graph, but I think that, I'm going to do that for each of these. So the domain remains unchanged. So I'll just write domain is going to be from -infinity to infinity. And the range is going to be from 0. I'm sorry about that. I was going back to what the original domain is, or original range. The range is going to be from -infinity to 0, where 0 is included. All right, next function, g of x. I see an absolute value, so I say, oh, okay, that's going to be the absolute value function. So that's my absolute value. Okay, cool. Now I see, all right, I'm adding a 2 on the inside, and then I am subtracting a 4 on the outside. So if you go back and look at it, you say, all right, in the inside, adding or subtracting something on the inside is my h. Adding or subtracting on the outside is my k. Now let's rewrite this in the form of x minus h. So if I do that, I have g of x equals absolute value of x minus a -2. And again, you don't have to do this, but I'm doing this to explain to you again. Notice that my h, this is the formation. This is the notation that we used for our graph, right? X minus h. So you always want to rewrite it as x minus h, or at least understand it to, understand. Oops, understand what exactly is the transformation there. So now I can say my h is equal to -2, and my k is equal to a -4. So what that means is now I am shifting the graph. So I can say shift, since h is -2, I'm going to say shift left 2 units. And I'm going to shift down 4 units because the k is negative. So let's go and look at this to identify our domain and range. So we have our quadratic graph here. So if I'm taking this graph, I'm shifting it left 2 units. My new vertex is going to be shifted left 2, but then it got shifted down 4. So it's going to be all the way down there. So it got shifted left 2 and then down 4, and then my graph should mirror my other parent graph. Okay? So you can see that, again, the domain is all real numbers. That gets unchanged. But you can see that the range has been shifted down, right? Now the lowest point is -4. So the range is going to be from -4 to infinity. So my domain is still -infinity to infinity. And my range is now -4 to infinity. All right. Next one, square root function. I see that square root function, so labeling this, I have square root of h is equal to the square root of x. Notice here I had a negative on the outside. That was my a. So again, what happens when I have a negative on the inside? That is going to be my b, right? And what does b do? When b is negative, that's a reflection about the y-axis. Okay, cool. And obviously, I'm adding a 1 on the outside. That's going to be my k. So I'll label this again one last time. So I'll say b is equal to -1, and my k is equal to a +1. So therefore, as I just mentioned, I just cheated there. That's going to be a reflection about the y-axis, and I'm going to be shifting up 1 unit. Okay, so let's go and take a look at this graph and kind of see how the domain and range is going to be affected. So here, remember, the domain is from 0 to infinity. Well, if I shift the graph, if I reflect the graph across the y-axis, now the graph is going to go to the left, right? You take this graph and you reflect about the y-axis, so now it's going to be going this way, and then also it got shifted up 1. So the graph looks something like this now. So that's important because the reflection affects the domain. Now the domain is from -infinity to 0. And now my range also got affected by the vertical shift. So since my graph got shifted up 1, the range, instead of being from 0 to infinity, it's now from 1 to infinity. So my domain is going to be -infinity to 0, where 0 is still included. And my range is now from 1 to infinity. Okay, so a couple things that I want, let's talk about that once we do a couple more examples. All right, so now I'm not going to label everything. I am just going to start talking about each of my shifts, and then again, we're just going to do a rough sketch. You can see some of these are not very fun to sketch, but again, we're just kind of getting the idea exactly of what's happening. All right, so here I have a negative again on the outside, so that's a -2. So I'm going to kind of do each one separately. So since that's a negative on the outside, I know it's going to be reflecting of the x-axis. So I'll just write, reflect x-axis. My a is now larger than 1. So since absolute value of a is larger than 1, that's going to be a vertical stretch. So I'm just going to do vertical stretch factor of 2. Okay, and then you can see this 1/5. Now it's important that I would usually put parentheses if I wanted that to be inside of the logarithm. So we can see that this -1/5 is outside of the logarithm. So therefore, that's just going to be a shifting down 1/5. Now that's not going to be fun to graph, but again, we're just sketching this, right? All right, so let's kind of look at, so we have a vertical, so we have a reflection of the x-axis, okay, so that's going to be reflecting about the x-axis. We have a vertical stretch, and then we're going to get shifted down 1/5. So let's kind of see what that does to our logarithmic graph. Okay, so the graph got reflected, right? So reflected about the x-axis, so now it's going to be something like that. it got stretched. So now it's going to be a little bit farther, and it got shifted down. So the graph is probably going to look something maybe like this. I don't know, something close. The important thing to understand is the domain was from 0 to infinity. By vertically stretching the graph, reflecting it about the x-axis, as well as shifting it up and down, did not affect my domain at all. So my domain is unchanged. Also, my range is unchanged. This graph is still continuously going up and continuously going down. So therefore, the domain and range of this graph, even with all these transformations, is unaffected. It's kind of cool. So I'll say the domain, again, is going to be from 0 to infinity. Notice 0 is not included because at 0 there's an asymptote. And the range in this case is going to be from negative infinity to infinity. All right, next equation, next example, y equals e to the negative 1/3. So now I have a negative on the inside, so I automatically kind of know, going back, that's going to be reflecting the y-axis. The 1/3, this one kind of tricks people up. We know that the 1/3 is going to be if it was 1/3 on the outside, that'd be a vertical compression, but it's when it's 1/3 on the inside, if you just go back and look at your notes, what you notice is that is going to be a horizontal stretch. So I'm just going to say horizontal stretch, and then I'm going to say a factor of 1/3. So let's kind of see how this affects this graph. So here's my e to the x. I got reflected about the y-axis. So the graph looks like that. And then also it got stretched, right? So it's probably going to look something like this. Maybe something like that. I don't know. Close. Close. Something like that, right? It's getting stretched horizontally, and it's got reflected about the y-axis. But notice a couple things. My domain is still the same. It's still increasing. It's still continually going to the left and continually going to the right. And then also my horizontal asymptote, which was like my bounding feature of my range, that got unchanged too. So just because I horizontally stretched it and reflect about the y-axis, that didn't affect anything vertically. So we can see that the domain is going to remain the same, which is going to be from negative infinity to infinity. And my range is going to remain the same. That's going to be parentheses because it is at an asymptote from 0 to infinity. All right, into the next one, we have y equals 2 plus 1 over x plus 1. Now this one can sometimes be confusing, especially if we have a number like that's not in the perfect placement. So what I could do here is just rearrange, why don't I just add the 2 over here? Like, it doesn't matter if it's 2 plus or plus 2, right? So in this case, you can see, oh, all right, that makes a little bit more sense. You can see that this is my k and this is my h. So therefore, I'm going to, remember, it's kind of like the opposite, like it's x minus h. So this is going to be a shift 1 unit left. And then it's also going to be a shift 2 units up. I don't want to write units, 2 up. All right, now the graph on this one is kind of interesting because it's really important for us to understand that reciprocal function has a horizontal asymptote, I'll get in close, has a horizontal asymptote at y equals 0 and a vertical asymptote at x equals 0, right? So if this graph got shifted, I'll use a different color. If this graph got shifted 1 unit to the left, that means my asymptote got shifted 1 unit to the left. So now instead of the undefined value being at 0, it's now at negative 1. And if my graph gets shifted 2 units up, my horizontal asymptote, instead of it being at y equals 0, is now at y equals 2. So that affects our domain and our range. Now my graph is not going to be that good, but that's okay. The important thing for us to understand, though, is the domain is now all real numbers except x cannot equal negative 8, and the range is all real numbers except y cannot equal 2. So now I'll just write in the domain is going to be now another. You could use this using set notation. You could write it like this, all real numbers such that x cannot equal negative 1. Or I prefer to write things using our interval notation, which we practiced. which would be from negative infinity all the way to 2, union 2 to infinity. So just showing you two different notations to write the domain and range. All right, last set, guys. We're almost there. So let's look at this 1/2 here. The 1/2 is on the outside. We're multiplying it. So we're multiplying by this 1/2 on the outside. So the important thing to understand with multiplying on the outside, that is going to be a vertical compression factor of 1/2. I am subtracting a pi, so therefore I'm going to be shift pi units right. Okay, so as we go ahead and take a look at that graph, we have a horizontal compression, so that means this graph is going to be kind of shrunk, and then also it got shifted pi units over to the right. Now, I know it's kind of confusing to look at this as far as understand, how that transformation would be or where exactly is pi, but if you actually kind of look a little bit in, you can see that this graph has an intercept at pi. So therefore, if I just kind of like recreated this graph here at pi, you would see that, that's going to be representative of our shift. However, I should mention, though, it was a horizontal compression, right? Or, sorry, vertical compression. So the graph only went up as high as the parent function. And that's a really bad representation, but hopefully you kind of see that the graph got compressed. Now, as far as, now this value does go up to 1 and goes down to -1. So it looks like if I'm going half of that, then it looks like the max and mins of this is going to be from 1/2 to -1, which doesn't affect the domain, but it does affect the range here. So we can see that the range now is going to be from -1/2 to 1/2, and the domain is unaffected because the graph still kind of follows the pattern. Did I not do the cube root? Oh, there's a cube root function. Okay. So let's go ahead and look at, so this graph here, so my domain is still going to be all real numbers. So that's negative infinity to infinity. And my range, though, is now going to be from -1/2 to 1/2. Okay. Last one, or next one, cube root function. So I guess I kind of stopped writing what the functions were, right? Didn't I? So this one is k of x equals the cube root of x. Now this one gets tricky because you can see that we have a b and we have a h. And if you remember, if you look at this formula that we provided, when I have a b and an h, notice how my b is factored out. And that's the right way that we're going to want to represent this. We don't want to represent this as b x minus h. We want to make sure that we factor this b out, so it's x minus h over b. Okay, that's very important for us understanding the correct values of the b. And we'll look at that in some examples later. So in this case, if I need to factor out a 2, notice that 2 does not factor out a 5. So basically factoring, though, is like dividing out. So follow me here. This new function, if I was going to rewrite this, k of x, can be rewritten as the cube root of 2 times x, right? 2 times x is 2x. And then 2 times what is going to give me 5? Well, that's going to be 5/2. Okay, so now we see that we have a b, which is 2. So my b, when b is larger, when absolute value b is larger than 1, that's going to be a horizontal compression. So I can say a horizontal compression of factor of 2. And then also I'm shifting the graph left 5 units. So left 5/2 units, sorry. Left 5/2. Or I'd say it's a shift, right? Left shift 5/2. Now if we're going to go and sketch this graph here. Where's that cube root function? There she is. So we have a horizontal compression of 2, and we got shifted 5/2 units to the left. So that's going to be like, somewhere over there, whatever else. And it got compressed. So it'd probably, look maybe something like that either way. The main important thing to understand, though, is the graph is going to continue going left and right. It's going to continue going up and down. So the domain and range are unaffected from these transformations. Since this graph since there was no restrictions on the domain and range to begin with, the transformations are not going to affect it. So domain is going to be negative infinity to infinity, and the range is going to be negative infinity to infinity. All right, and last but not least here is I have another one with 1 minus x cubed. So again, we want to apply the same operation here. We don't have a b in this case, or it's not written in the same format. So again, to rewrite this problem, what we'll want to do is just write it in the notation that we have been provided. So I can write negative x plus 1 cubed. And then we notice, I don't like writing it with the b. I want to make sure that b is factored out. So I factor out the b, and I get x minus 1 cubed, second parenthesis. So therefore, again, we can see we have a reflect the y-axis, and we have a shift 1 unit to the right. Okay, so let's go and take a look at the graph here. Here is the cube root function. And notice that this cube root function is unrestricted on the domain and range. So I'm going to still reflect it, 1 unit to the, what was it, to left or right? I forgot. Dang it. It's 1 unit to the right. So I'm going to shift it 1 unit to the right, and then also reflect it about the y-axis. So the graph probably looks like this. But since my domain and range are unrestricted, that's not going to affect the domain and range. So I do want to kind of summarize a couple of these things. Oops, that's getting into the next example. So my domain, I don't know why I'm writing domain here. My domain is going to be negative infinity to infinity, and my range is going to be negative infinity to infinity. So let's kind of summarize here. Again, if my domain and range are unrestricted, then I don't need to worry about the transformations. They are not going to affect the domain and range at all. If my domain is restricted, so I have, it's not going to negative infinity to infinity, then the only thing that's going to affect the domain is going to be a reflection about the y-axis or a horizontal shift. If my range is restricted, the only thing that's going to affect the range is a reflection about the x-axis or a vertical shift, h and k. And I'll probably write these down in my notes. I didn't add them onto this, but now that I've been teaching this, I kind of see that I could add some things. So again, the transformations on the outside, those affect the range. The transformations on the inside, those affect the domain. Now again, that's only if the domain or range were restricted. If they're not restricted, you don't need to worry about that. But just notice outside, that's shifting the graph up or down or reflecting it up or vertically. And inside transformations are shifting the graph left or right or reflecting it left or right. So that's just kind of something really important to take away from this. It's really important to make sure you know these basic transformations. As I mentioned, it is fair game from now on. And now what we'll do is kind of look at the same thing for transformations, but just kind of apply it in some different ways to so it's not so much maybe straightforward. Maybe you have to look at it again. So we'll go ahead and get into that in your example.